Lean. So our speaker for the next session would have been Asya Fisher. Unfortunately, she has taken very ill and she cannot join us. But the good news is we do have quite a few experts in generative models on our committee. And with that, it is my absolute pleasure to introduce our speaker for this session, which is our very own Shakir Mohamed. Okay, so in that case, I think I can skip the introductions. I'm sure everybody knows you. Maybe I will just say that Shakir has been an absolute force with this Indaba right from the very beginning, about 2 years ago. I want to say that it has been an absolute pleasure for me to be a student of Shakir's School of Management. And I can also say that I'm very happy to see that Shakir is finally wearing his red T-shirt. I think this is the first time I've ever seen him wearing a T-shirt, so we are very proud of that. Shakir, thank you very much.
Thank you. Okay, it's really great. Asya really wanted to be here with all of you, but I decided to step in. So when I'm not busy doing work with the Indaba, I work actually in this area. This is the main focus of my research that I do every day. And I wanted to split sort of this 1.5 hour session into 3 bits, a bit about foundations of probabilistic thinking, a bit about some tricks, and we're going to do a bit of mathematics and manipulate probabilities together, and then we're going to think about some of the currently popular algorithms in generative models. And I'll just say that one of the reasons I love giving this talk and giving these kinds of talks is that every time I do them, I get to rediscover the field of machine learning. And I get to rediscover with you why we love doing what we do, why machine learning is so important to us, and how together we can do more if we push the boundaries of our science. And one of the ways that I think about machine learning is that it gives us a pathway to think about moving from principles to products. And this is the kind of thing that we all want to do. We want to be able to move from those foundation principles, which involves probability theory, which involves Bayesian analysis, hypothesis testing, estimation theory, asymptotic theory. These are the foundations of your mathematical training and many other things, differential geometry, calculus, category theory, measure theory, etc. And then from those principles, we then build those kind of informational quantities. We look at things like uncertainty. We look at information gain. How is it that I accumulate information? We look at questions of causality. What causes what? And then we can look at questions about how we can make predictions on data that we have not seen. And based on those informational principles, we can then move to the task of reasoning. How is it that we can do planning based on those informational and other principles? How can we explain data sets and provide explanations for why certain things are happening in the world? How is it that we can learn rapidly from very small amounts of data? How is it that we can simulate the future evolution of the world and what may happen in the future? How can we understand that the world has objects, objects are related to each other, and how those relations can evolve and change over time? And ultimately, then we also can think about those applications that we want to use for machine learning to uplift our continent, those assistive technologies that help us do text-to-speech when we cannot speak, those ways of advancing our science, whether while working with the Square Kilometre Array telescope or looking at the Large Hadron Collider to find new fundamental particles, whether we're thinking of climate and energy, or we are trying to address those critical, complex challenges of healthcare systems. And each of us will be navigating this pathway in very different ways. We will start at a different place. Some of you will start thinking that I want to work in healthcare, and then you will need to work backwards to figure out what the principles, those informational quantities, those kind of reasoning aspects are. Some of you will be more theoretical. You will be thinking of asymptotic theory and how your asymptotic theory comes together to explain when something is correct and when it is not. And others will be thinking at other different levels. And we will all navigate this in different ways, and this is why we need to be together, so that when we exchange information, we understand better the different ways and different pathways. And so I'm going to show you one way of navigating this hierarchy using the tools of generative models. So the first part is going to be about foundations, and we're going to recap just a little bit about the things you heard yesterday and over the past 2 days, actually. So the two things I want you to take just from this part is build a language to think about the philosophy of machine learning, the kind of structures we use to think about things, and sort of we'll work through a bit of that. And the second bit will be what I consider a very important tool for thinking about machine learning, which is the paradigm of models, inference, and algorithm, and how you use that to structure your thinking as a machine learning scientist. So let's think a little bit about probability. And if I were to ask you, if we were in a smaller room, we would have a debate about the definition of probability. And maybe some of you would know there are at least 8 definitions of probability, so you can choose your favorite one, but these are 4 that I like. One is what we call the statistical probability. This is the one you basically learn the first time you encounter probability. It is the frequency ratio of items as they occur. And that's a very good definition of probability, what we would call the frequentist view of probability. Then you have another view, which is called the logical view of probability. Like we have logic, which form from axioms and deductions, we can use probability as the degree of confirmation of a hypothesis based on a logical analysis. And probability theory is a general theory, so everything related to logic generalizes and is subsumed through the theory of probability. And many of you who are logicians will be using that view of logical probability to assign uncertainty to logical deductions and hypotheses. A view you won't see very often these days is probability as propensity. Let me just do that. And propensity just means the ability to make predictions. And so propensity theory and the propensity probability theory is all about probability as it is used for predictions. And actually many parts of machine learning are in fact just probability as propensity, because we often think about prediction as our principal task. But I think one of the most important definitions of probability is subjective probability. Probability is a degree of belief. But whichever definition of probability you are interested in, probability is the tool which is sufficient for the task of reasoning under uncertainty. And we live in a world that is full of uncertainty, and so probability will become the most important tool that you have in your arsenal as a machine learning scientist and for any application that you're going to think about. So the top 3 definitions will all have certain paradoxes. They will have certain problems, which is why I asked to always use the subjective probability view. The subjective probability view is general enough that it subsumes all the other definitions of probability and addresses some of their sort of quirks and paradoxes. So again, this definition of probability is a measure of belief in a proposition given evidence. And I think this word is the most important one. Yabebal spoke to us yesterday about this, that it is a description of a state of knowledge, and evidence is important. And just given that thing, there are 3 important implications. One is that there is no such thing as the probability of an event. A probability is always dependent on the evidence that you have. So so that means it is inherently subjective, and it depends on the believer's information. So if 2 observers have different information, they will have different probabilities. And this is a very important point. And this is where paradoxes of probability sort of disappear, because it always depends on evidence. Yabebal said this in the other way, that if 2 observers have the same information, they will have the same probability. So these are the most important things. So always keep this definition of probability in mind as you are working through things. So just some notation that I'm going to use. We'll look at these basic probabilistic quantities. When I talk about the probability of a random variable x, I will use this notation p of x. Sometimes I get a data set and it has a probability distribution. That probability distribution will be unknown to me. But it has a true probability distribution, and so I'll call that p star, this unknown but probability distribution that exists in the data. And sometimes I just want to make a different probability distribution, so I'm going to use the notation Q of x instead. The axioms of probability are that probabilities are always greater than 0, and that when you sum over all possible events that could occur under that probability space, they will sum to 1. And for the rest of this week, I will ask you to work with this definition of probability. This is what you could call a classical definition of probability, but I know there are some of you here who are quantum probabilists. The definition of quantum probability asks you, there's no reason to think for things to be greater than 0. There's no reason for things to operate in this way, and the quantum probability will ask you to create a different probability theory, and it's a fun area and one of the interesting areas of machine learning research to see how we push into that area. The Bayes rule that you learned, Bayes rule is a very simple rule. It is simply the rule of how we invert probabilities. If I have a probability distribution of x conditioned on z, and I want to go to the distribution of probability of z conditioned on x, Bayes' rule is that rule of inverting probabilities. And when you think of Bayes' rule, think of nothing else than that, and all the other complexity will just be much simpler. We will often parameterize conditional distributions. So this notation, P of x given z, hides a lot of things. It doesn't tell you exactly how z is dependent on x, and sometimes I will just put this semicolon theta or subscript theta to let you know that there are a set of parameters theta which will relate how z influences or describes x. Expectation, and just write this somewhere in your piece of paper, it will be the thing that I will use everywhere, that when I write expectation of a function x, and this is function x, and this function may have its own parameters phi, that expectation could be under some other distribution p with its own parameters theta. And that expectation is simply the integral of p of theta of x given z times the function x with its parameters theta. Expectation will be the most important quantity that we will use in machine learning. Everything in machine learning is effectively about computing expectations of this form, because the function can be your neural network, this probability distribution can be your data. This is what Mustafa told us was the empirical risk principle. And so everything is going to look like this, and all of machine learning, in fact, is going to be coming to finding ways of manipulating this integral and computing expectations. And of course, one of the other important things is always to compute the gradient. The gradient of f, so that's why I'm going to use the symbol nabla, with respect to the parameters phi, is just the collection of all the partial derivatives of f at those parameters phi. And so these are multivariate quantities. So we're going to use all of these, so just make a note of those notation. If it's unclear, then just shout. Okay. There are effectively 4 principal statistical operations to think about. The first one is what we would call data enumeration. We are all working in an area where data is important. We need to collect data. This data enumeration is that process of collecting our data. How did we collect our data? About whom did we collect our data? What bias is in that data? What specific sampling categories, what exclusion criteria we use? So data enumeration is very important. And from that data enumeration, we can do 2 types of operations. The first is what we can call summarization. Summarization is the way of collecting all your different data points together, and then to say, how is it that these data points are the same? How is it that they are related? What are their underlying trends? The opposite of summarization is called comparison. Can we tear our data apart? How can we say how one data point is different from another data point? And these 2 principles of summarization and comparison are the 2 bases of thinking about learning in machine learning. And of course, the way we need to, once you have data and you have a question of summarization or comparison, the way you can do that is given by this process, what we call inference. You will hear this word, statistical inference. Inference is the process of combining the data that you have to the model that you have designed. And that is basically what inference is, how you connect your data to your model. And so for each of these 4 categories, something different will appear in the space of machine learning thinking. When we think about data connecting to summarization, we call that process modeling. How is it we can describe our data? What are the things that we use? When we think about data and then asking how things are different, we'll call that experimental design. And we do a lot of experiments, design of experiments to see how things are. When we think about this process of inference in a statistical model, we will often call that estimation. If you are a statistician, you will call that estimation. And if you are more of a machine learner, you will call that learning. And then finally, when we think about inference in the process of comparison, that is where we think about hypothesis testing. How can we test how one thing is different from another, or say somehow with a probabilistic statement that something is different from another. So these are the 4 basic operations that will run the thread through any kind of machine learning that you're going to do. And it's often useful to think about them, and actually, if you find yourself spending too much time in one sort of segment, you can sort of jump to another bit, and in there you will find a set of algorithms, computational tools, probabilistic tricks that you can use to manipulate in other ways. So this is sort of a personal view, but when you see these 4 statistical operations, many of you will begin to think about this more general question about artificial general intelligence. And how is it that our machine learning is going to help us move to that point of designing this somehow more general purpose learning algorithm. And AGI will be the most refined instantiation of these 4 statistical operations. And that's why knowing and mastering and manipulating these operations becomes critical. And within those 4 statistical operations, the process of inference becomes the most central of those. Because again, it is the way of connecting evidence, experience, and data to kind of models of the world. And so the core questions of AGI will always be those questions of probabilistic inference, which is why it is one of the largest areas of any computational science. So how is it that you are going to think about your machine learning practice as you continue to develop and as you continue to grow? And I hope that every single one of you will first go through a human-centered approach, that you will approach your machine learning always thinking that there are humans involved and that we build these machines thinking about humans, and that we always work together through interdisciplinary thinking, that we are machine learning scientists, we are probabilists, we are engineers, but we can work with our social scientists, our bioinformaticians, our climate scientists. And when we put those teams together, that is how we will work. And this is sort of one of those frameworks of thinking that I really like. It comes from cognitive science. It's called Sun's phenomenological levels. And Sun's phenomenological levels asks us to think about how we create this human-centered process. It says there is a physiological level, there is a substrate. How am I doing my computation? Is it in brains, in neurons? Is it on a CPU? Is it on a GPU? Is it in the cloud? How is that? You have those componential components, which are, what are those core elements? How do I make prediction? How do I represent uncertainty? There are those psychological components. How do I do planning? How do I use memory? How do I combine memories with planning to take action? And how do I do self-assessment and self-evaluation of my decisions? And finally, there is a sociological element, that you as an agent don't exist independently. There are other agents and other things to consider, other humans, the environment, other kinds of systems you are interacting with. So Sun's phenomenological levels I consider very important as a basis for thinking about human-centered machine learning. But for the machine learning core, which is what you're here to learn this week, I will always ask you to think of a probabilistic but pragmatic approach. So most of what you will learn uses the framework of what I call the architecture loss framework, and I'll just briefly summarize it for you. But the most important one that I think is useful is to consider what is the model, inference, and algorithm paradigm. And I want you just to be able to embed this kind of thinking and use that. So the architecture loss paradigm is everything you've seen up to now. It asks you to build a computational graph. And this computational graph represents the kind of sequence of computation. So this is a classifier that we learned about yesterday. It can be a convolutional model, as Naila spoke, or a fully connected model, as both Nando did, or any of these. And Nando described this process of layered structures, these building blocks. That building block view is this process of creating a computational graph. What you then do is attach a loss to this computational graph, and then based on that, you can do what is called error propagation. And of course, doing backpropagation in a neural network is only one instantiation of this architecture loss process. Another way of doing this is what we call factor graphs. If any of you have done other courses, a factor graph also instantiates a computational graph, and then its error propagation has a different kind of method, which is called belief propagation. And so we have many. This is one of the most fundamental ways of thinking machine learning. You should always be able to do that. But you should be equally flexible to do another way, which is what I call the model inference algorithm paradigm. So all of machine learning can be thought about in 3 ways. You have a model, and the model is the thing that describes the data that you have. The model is the thing that you are going to use to make predictions. The model is the thing that you're going to use to unpack, question your data. For any given model and data, you will need to think of a learning principle. How is it that that data will then get influence into your model? And there are many different learning principles. And for any model, you can choose any different learning principle. And for any learning principle, you can do any model. So when you combine them, you get many different things. So the combination of a model and a learning principle is what will give us an algorithm. And an algorithm is, this algorithmic view is that architecture loss view from the previous slide. So spend a bit of time doing some exercise to jump between these 2 points of view. So let's do a few examples of models. So you have many different types of models. Some models are called directed and undirected graphs. Most of the models that we look at these days are in this class of directed, where where the direction of the arrow has meaning. Sometimes we have fully observed graphs. We're going to talk about that a bit later. We have other models which are called latent variable models, which introduce some unobserved quantities. And then we have other classes of models, parametric, non-parametric, and semi-parametric. And all these different types of models they are fully compatible. So you can have undirected, non-parametric models with latent variables. This is very easy to do. And so all of these is just different views and different ways of understanding characteristics of your models. Then we have learning principles. Learning principles, as I said, are one of the most important things. They fall under this rubric or heading of statistical inference. And you have roughly 2 classes of statistical inference. One is called the direct statistical inferences, and then you have the opposite, which is indirect statistical inference. Direct statistical inferences are direct because they always try to directly target the probability of data. And we're going to look at an example of that later. So you have many examples of direct inferences that you have looked at. Maximum likelihood, which is the one you have all used, the backpropagation when you created the squared error loss. That is about maximum likelihood. Later we're going to talk about variational inference. But there are many other methods. Some of you, I've seen from the posters, are doing Markov chain Monte Carlo. And there are other methods like expectation maximization. The physicists in the room may know a few cavity methods. So there are many different areas of direct statistical inference. And on the opposite end, we have indirect statistical inferences. Rather than looking at the likelihood and taking its derivative directly, we are going to try and indirectly know the likelihood. So the 2 classic ones are called two-sample testing and the method of moments, which is 150 years old. These days, we have approximate Bayesian computation. There are other methods from transportation theory, maximum mean discrepancy. And we're going to look at one of the ways of doing indirect inferences later on. So then, for any given model and any given inferential principle, you can put them together in many ways. So here are 4 examples. If you have a convolutional neural network, that is your model. And if you have a learning principle, which is the penalized maximum likelihood, then you can implement that in many different ways. And each implementation gives you a different algorithm. And it's important to keep this in mind because how you will do your comparison, how you will fairly assess how things should behave and how you will compare to things in other fields entirely needs you to control what is the model, what is the inference, and what is the algorithm. So here you can implement it with different optimization methods, with ADAM, with SGD. You can use different regularizations, and you need to control in that way. So you need to use the same model, the same inference, and then you can change other things of the algorithm. Or you fix the algorithm, change the inference. Here's a model you won't see very often, and we won't talk about it at this Indaba, which is the restricted Boltzmann machine, and we can do maximum likelihood, and there are at least 4 different algorithms, contrastive divergence, variations of that, persistent contrastive divergence using natural gradients. 2 that I wanted to talk about later. If you have latent variable models and you choose a principle of inference called variational inference, then you can implement that in many, many different ways. The classic one is called the variational EM algorithm. There's also expectation propagation. We have other methods now called approximate message passing. We can do this through the variational autoencoder algorithm. And the last kind of model is what is called the implicit generative model. If you use the principle of inference called two-sample testing, you can then implement that in many different ways. One way is called as unsupervised as supervised learning. You have another class of methods called approximate Bayesian computation. You have another class of methods, the algorithm called the generative adversarial network. So there are lots of these kind of things. So I want you just to take 2 minutes, discuss amongst your partners any machine learning algorithm that you know, and just talk about that algorithm with your neighbor within this model, inference, and algorithm paradigm. And I'm sure there are questions, so there are mics on both sides. If you have a question to ask at this point, please walk over to the mic, and then we'll take those questions and then move on to part 2. So do a quick discussion, and we can feedback afterwards. Okay. So, what questions do you have? No questions? Should we wait? Does anyone want to go over to the mics just to talk a little bit? Okay. No questions? Then we can move on. So we're going to do a little bit of probability theory and a bit of mathematics and a bit of derivation in this section. So please bring a piece of paper, bring your notebooks together, and we're going to go through the steps very carefully, and at some point you're going to have to do some manipulation. So the point of this part, I've given a much longer lecture, so you're going to get a bit of a shorter version of this, is for you to build what I call probabilistic dexterity. If you are able to manipulate probability distributions, then you will be able to do a lot of things in machine learning. And so the things that I want you to get out of this is that I want you to begin to develop the tools to manipulate probability distributions. And we're going to look at 4 questions of manipulating those probability distributions. And then finally, I want you to understand that the things we talk about in machine learning, the kind of language we use, is not unique to machine learning. That the things that we talk about here actually maybe already exist in many other areas, like statistical physics or economics or operations research. And so I want you to build a language to jump between these fields. So when you read papers in those areas, when you work with people in those areas, you understand the language that we have is transferable and we can connect between these places. So as I said, the core question of machine learning will be those inferential questions. And so I want you to build probabilistic dexterity and what that means. So there are many different kinds of probability questions. This first one is called the evidence estimation. If I have a joint probability distribution and I want to integrate out z, so there's another random variable z, I just want to know p of x. How do I do that? This distribution is called the marginal probability distribution, one of the most important integrals to be able to compute in machine learning. As I said, the main question we are going to focus on is what is called moment computation. How can I compute an expectation of a function? And sometimes it will be a conditional moment computation, which is why I'm putting the condition on x. There's parameter estimation, what you call learning, when we're doing backpropagation in convolutional networks, when we were doing learning in the sequence-to-sequence models yesterday with NLP, we were doing this problem of parameter estimation. And sometimes you will just compute the mean of this distribution, and sometimes you will want to know the entire distribution. There is the problem of prediction, what many people want to do, and then there is the problem of planning. And later today, when Katya is on the stage, she will talk to you about this problem of planning. How can you compute a probability distribution of actions over some cost? And then there are other kinds of questions, hypothesis testing. If I have 2 hypotheses, how do I assess them or compare them? And if I wanted to do experimental design, I'm in an actual physics, I'm simulating molecules, I am designing new kinds of physical apparatus. How do I assess the information that I get and decide where to do a next experiment? And so the first trick that I want you to use or learn is called the identity trick. And the identity trick is the most important trick you will learn. It is the trick that if you ever have an integral in some probability distribution and you want to transform that to an integral of a different probability distribution, this is the trick that you're going to use. So let's say we have this integral. It's an integral of p of x times some function f. So that is the expectation of the function f under the distribution p. I don't want to use this integral under the distribution p. P may be something I don't know, or it's something complicated that I can't simulate or sample from. So I need to just change this so I can do it with something that I know how to do. So the identity trick comes in, and it's going to let us rewrite this integral with equality. It will be the same integral, but I'm just going to find a way of rewriting it as an integral under some new distribution q. And that new distribution q is going to be something I know. It's a Gaussian distribution. It's going to be something I can easily sample from. I know everything about that distribution q. I'm the controller, the manipulator of that distribution. And this is why that identity trick is so important, because it lets us change any integral to any other integral that we want. And the key way to do that is by introducing a probabilistic 1. When you multiply by p of x and divide by p of x, that is a 1. And this single trick will let you do many things. And we're going to use it at least 2 times in the next 30 minutes. So let's manipulate this integral together. The first question is the integral problem. Can I compute the integral of probability distribution p of x given z and integrate out the variable z? So if I apply this identity trick, I'm just going to multiply by 1, and I'm going to use the distribution q instead. So multiply by q, divide by q. The integral is exactly the same. There's no difference. Then I'm just going to recombine the terms. So there's a p of z here at the top, and there's a q of z at the top. So that's what's in this blue box. And then there's the q of z. And if I just rewrite this in that expectation notation, this is the expectation under the distribution q of z times this new modified probability distribution. So now this is a much easier thing to do, but there are some things to think about. You all know that dividing by 0 is a bad thing, so make sure that now that I've introduced q of z, that q of z is never 0 when p of z is not 0. If that happens, things are going to blow up when you code it, and it's just probabilistically incorrect. So make sure that you always maintain this condition that q of z is going to be greater than 0 whenever the product of p of x given z times p of z is there. And the q of z, the point of the trick was that q of z must be something that you know and can manipulate. So don't add a q of z which is not the optimal q or not the q that you want. And so with this trick, we're going to do one of the first things, which is, and I want you to learn this word, it's called estimator. So here's the expectation that I want to have, and creating a Monte Carlo estimator of that integral means sampling from q of z and then evaluating this thing inside the brackets at the value of z, so z, where z is the sample. And this ws is just called the importance weight, and so it's just p of z times q of z. So this is one of the most important things you'll do, and let me just say a little bit more about this concept of an estimator. The reason it's called an estimator here is that I'm going to apply this kind of Monte Carlo trick where I'm going to rewrite the integral as an average over a set of samples. So this is an average over s samples of this. And you always want an estimator that starts of this form. So when I want to create an estimator, I need to create it as an expectation of some distribution that I can sample from, or some function I can evaluate. And so this is, we're going to rewrite a few other integrals in this form of an expectation of a distribution that I can sample from and then manipulate. And then if I have it in that form, I can create an estimator. And the properties of estimators is that they are unbiased. You will get the correct answer. And if you send s to infinity, you will get the true answer. And so this trick is used everywhere. We're going to use it to manipulate some stochastic gradients later on. For those of you that are probability theorists, you would have used this trick to derive probability bounds and prove the rate of convergence in the central limit theorem. And later on, maybe you will see this, but one of the core questions in reinforcement learning are about policy corrections, and one of the key ways of doing policy corrections is by using this identity trick. Are there any questions on that? Do you want to go over to the mic? There's one on both sides. It's going to be a bit, shout it out. Shall I stop here? in the typical application, you know everything. So let me start again. You know P of x given z. This is a thing you decide. It's a Gaussian distribution. You also know P of z. It's a prior distribution. Maybe it's a different Gaussian. Maybe it's something else. But you do know them. But because of the way they are related, you may not know how the product gives you the posterior distribution. And because there may be... So again, as I said, this conditioning notation hides a lot of things. Inside this probability distribution may live an entire neural network. You may decide that the relationship between z and x is given by a complicated neural network. In which case, the thing you don't know is the integral. You won't know how to compute the integral itself. So this is why we're doing this manipulation. So when you do this series of manipulations, now you get to this point. You do know this conditional distribution, because that was the thing you chose. You can evaluate it. You do know this prior distribution, and you chose Q of z. It's something you can easily sample from. It's just manipulating the computation in a different way, but also avoiding doing this top integral. This is a different integral. This integral is easier to compute because I can do this Monte Carlo estimator. Is that sort of clear? Another question around the identity trick? Yes? Oh yes, let me explain that notation. So this is called a graphical model, and the graphical model is just a way of representing these conditional probability distributions. So when I write this probability model of P of x given z, this arrow shows you this is probability distribution x, condition on that probability distribution z, and when they are circles, they are random variables. So this z in a circle means that there is a distribution P of z, which I am deciding, and the circle on x with the arrow to z means that this is a P of x given z. So this is how I write that notation, and I use that everywhere. So circles are always random variables. Arrows indicate directions of conditional probability. Another question on the identity trick. Yes? You are close to the mic. Maybe you can try that.
So earlier you were saying it made the integral easy to compute. Is this also applied to computing the integral numerically, or are you sometimes interested in like a closed form solution?
So the question here is about, is this a trick for us to compute integrals numerically, or is it sometimes about closed form solutions? So the question that the other person asked was, what do we know and what we don't know? And the reason to use this trick is when you, when both of what you said is not possible. When you cannot compute the integral in closed form, and most times you will not be able to compute the integral in closed form. The only time you're able to compute the integral in closed form is when there are two Gaussians, basically. So that situation will almost never occur in modern practice. And then when you compute it numerically, the other key thing is that the dimensions of these random variables is very large. So if you are working in one dimension or two dimensions, then you can use quadrature, for example, and you can compute the integral numerically. But as soon as you move to 3 dimensions, 10 dimensions, quadrature no longer works. And so then you cannot use that. It's the worst thing you can do almost to compute an integral in high dimensions. So the important sampling trick is a way for us to compute high-dimensional integrals for both which we cannot compute numerically, and we can do that. But the numerics is different. Now I'm transforming this into a numerical, which is an average by Monte Carlo sampling. I sample from this Q of z many times, s times. S can be 1 or s can be infinity, and then I average the computation here. And the accuracy of the computation of this integral is related to the number of samples s, and in fact it grows with 1 over the square root of s. And so you actually need many, many samples to get a very accurate estimate of this integral, and you can make it much more accurate by choosing the correct kind of Q, or a good Q. And we can talk offline a lot more about adaptively learning Q, and another trick will give you another insight. Another question on the integral trick, on the identity trick. Was there someone up there at the back that I missed? Yes? Yes. So the question was, just to be clear, when can we use this trick? When we can use this trick when we cannot compute this integral directly. We don't know it analytically. And quadrature in low dimensions is not something we are not working in a low-dimensional space, in which case quadrature can't be done. Yes, and then also it just lets us only work with the things we know, which is the conditional distributions, and because we know those because we designed the model. It's not with the posterior distribution, which we don't know, or the marginalized distribution, which we also don't know. One more question on the identity trick, yes? So f of z in this graph is this function p of x given z. Sorry, I just swapped the notation. So yeah, there's always some function you are usually let me just go back. Here, this is the integral of a function f times p of z. So when you read that in this, you can see here the function f is p of z, which is this line. You have the prior p of z, which you have chosen, and then you have q of z, which is the thing you are manipulating. And by controlling p of z, you can control. So you just shift q along, and then you estimate the integral by Monte Carlo. Okay, I think that was a good set of questions. Any more thoughts, thinking about just reading the integral even? We can spend a lot of time, as much time as we need to, just on that. Okay, let's do another trick. This trick is one of my most favorite ones. Actually, they're all my favorites, but this one is particularly beautiful. So this is called a bounding trick, and there are many, many bounding tricks, but this is the bounding tricks of all bounding tricks. And what it tells you is from convex analysis and optimization, and it tells you that if you have a concave functions are functions like this, they have a peak at the top, then you can take a function of an expectation is always greater than or equal to the expectation of the function. So you can move the function through the expectation, and it gives you an inequality, a bound, in the way that they are related. So this is one of the most important things you can do, because we are always going to be doing some kind of manipulations of a function of an integral or an integral of a function, and we want to shift them back and forth as we go. So logarithms are concave functions, and actually because of this reason, this is one of the reasons we always use the log probability everywhere in machine learning. So this is the log of this integral. So log is this function f here in this notation. That is the concave function. Then we're going to do the expectation. The expectation is under the distribution p of x, and this random variable x is this thing in the green box, which I'm just representing more generally as a function, g of x. And I can now move the log function through the integral. This is why this trick is so important, because logs can magically transport themselves through an integral, and now this becomes an integral under p of x of log of g of x. And now this looks like the form of that we can make an estimator, and so this is why it's very important. It is now a form of an expectation of a function under a distribution, which means the Monte Carlo theorem from the previous slide can be used, and then we can apply the identity trick, and then we can do several other things to it. So this becomes pretty important, and this bounding trick you'll see everywhere. You use it in optimization to prove the rates of convergence. We're going to use this in variational inference, which is one of the core methods of inference in machine learning. And if you're working in Monte Carlo theorem and probability theory, there's a famous theorem called Rao-Blackwell's theorem, and the way you prove Rao-Blackwell's theorem, which is how you get the minimum variance model, is by using this trick. And you have many other kinds of tricks. If you're already studying optimization, you would have studied the trick called Fenchel duality, and Fenchel duality is a way of designing these kind of convex bounds. There's Holder's inequality, which is a fun one to learn about, and if you are using transportation theory, then this Monge-Kantorovich inequality is another good one to use to manipulate integrals from this form and get bounds. So let's do another bit of calculation together. Please bring your pieces of paper. We're going to do it. So we have our same integral problem. Compute the marginalized probability p of x, which is the integral of p of x given z times the distribution p of z, and I'm going to integrate over the dimension z. Z is a high-dimensional quantity. Imagine it is 10,000 dimensions. It is not something you can do quadrature for or numerical integration. So we're going to have to do some kind of Monte Carlo integration. I know the distribution p of x given z. I know p of z, but because they may be defined in terms of neural networks, I won't know the posterior probability of p of z given x. I won't be able to compute the integral in closed form. So this is why I'm going to need some kind of trick. So I'm going to use the identity trick again, because that's the way I can manipulate probabilities. I'm going to multiply by 1 of q of z, divide by q of z. Then I'm going to reshuffle the terms exactly as we did in the previous slide to get the importance weighting. So now it becomes the integral of this function, p of x given z, times p of z divided by q of z multiplied by q of z. I hope this line is clear. We did it in the previous slide. We're just remanipulating the terms. And now in the last slide, we use the Monte Carlo integration theorem to manipulate this line. Instead, we're going to use this trick we just learned, which was called the bounding trick. And if I use log of this quantity, then I'm going to take log through the integral. So log of p of x, because of that bounding trick, is going to be greater than or equal to the integral of q of z times log of this function. Right? Scribble it on your paper. Make sure you can do it. Let's just stare at it for a bit. Right. Okay. I'm just going to split the terms because log is one of those magical things that lets us split things. So I'm going to do the same integral of q of x, q of z times log of just this first part, p of x given z. And then I'm going to separate this ratio. And what I'm also going to do is invert it. And so instead of p of z given q of z, I'm going to write of q of z divided by p of z. And because I'm going to flip it and I have the log, I'm going to add a minus sign. So that step is just from the property of logs. And the reason I'm doing that is because I wanted to write it in this way. I want to say that this is a lower bound to this quantity and is now written as an integral of expectation of q of z times this log probability of p of x given z. And then this other term which has emerged is a famous term. It's called the Kullback-Leibler divergence, the KL divergence, between the distribution q of z and p of z. So if ever I write somewhere KL, q of z to p of z, it's this integral of q times the log of q divided by p. So this is one of the most famous inequalities that we have. It is because of this inequality that we now are able to know the energy levels of the electron. If there are physicists in the room, they will tell you how to do a variational method to compute those energy levels. But also this has been one of the workhorses of machine learning for the last 5 years. And so it's very important to know this. So if you were just doing maximum likelihood, let's just stare at this, you would only have this first term. And so this manipulation of the integral has shown us that there are other terms which when we use our mathematical tools and tricks, we're going to get out of that. So let's just spend a little bit of time. Are there questions about the bounding trick? Yes, we're closer to the mic, so maybe we can have you try that one. And are there any other questions? And if you have a question, you know, if that burning thing is coming, then that side as well. How about you? I'm being lazy with notation. dz is always there. So these integrals are always against the space of dz. So add a dz here, add a dz there. More questions on the bounding trick? Confusions? Is the derivation clear? Yes. There are no stupid questions. Okay, that's a great question, actually. This quantity p of x is called the marginalized probability, but it is also called the evidence. If you know this quantity, what does it mean? If x is data, then p of x is the probability of your data. If you know the probability of your data, you are like God. You literally know everything. You can make any prediction, you can compute any moment, you can do any expectation, you can do any parameter learning that you know. So because knowing the evidence of the data, the probability of the data is so central, that's why this integral becomes almost the most important question. And that question is called the evidence in this case. And because we are using this bounding trick to create a bound in the evidence, this now becomes an evidence bound or a lower bound. But we can use those other tricks to create other kinds of evidence bounds. This is a lower bound. If you use Holder's inequality, you would have got an upper bound, and you can create other kinds of bounds. But bounds are very important because it's always lower. So if you optimize, they only go in one direction. So it's pretty important. More questions? Yes? Okay, so Ulrich is asking a question about optimality. A question about when is this not a bound, but when is it exact? And this is a very important question because The point of doing machine learning is going to learn this distribution Q so that we get the exact bound. We try and make the bound tight. We make the difference between the truth and the thing on the left-hand side and the right-hand side be 0. So that's all about this choice of this distribution Q. We're going to spend a bit of time at the end talking about this distribution Q. And the optimal Q distribution is going to be the posterior distribution of P of x given Z times P of Z divided by P of x. And to show that, I have another set of slides online where you can learn about variational calculus, and you can use variational calculus to show what the optimal distribution Q is. Variational calculus is just a fancy way of doing calculus on functions. So if you use the calculus on functions, you take the derivative of this integral with respect to Q, you set it to 0. The optimal Q will be this posterior distribution. Does that sort of answer your question? More questions on the bound trick? Yes? Okay, good. So the question was, so now that we have this, this becomes our objective function, and yes, you're exactly right. This becomes our objective function, and there are two things in this objective function, just to note. We're going to want to learn Q of Z, which is the posterior distribution, or some approximation of the posterior distribution. But there will also be parameters living inside P of x given Z. So if P of x given Z is a convolutional neural network, the parameters of the convolutional neural network live in here. So there are two types of parameters that will have to be learned here. And so this is why this is a bit special, that now there are two things. You're going to learn the parameters of your convnet, which is this probability distribution, but I'm also going to try and learn this other distribution, which may have its own parameters. So the question was about what kind of things, what kind of distributions is Q? And so you can use simple distributions like the known primitive distributions, Gaussians, etc. But as we said, the best Q is the Q that is closest to the true posterior distribution. And so we're going to use this objective to find a Q in the family of things that we're doing, which is closest to the truth. And the research question that we face in 2018 is how can we build Qs that are arbitrarily flexible, arbitrarily powerful? And I'll make a quick comment. One more question. Yes, Maria. Yes? Mm-hmm. Okay. So you are thinking about this line. So let me just unpack. So Maria's question is about in which situation, how does this computing the evidence help us solve the learning problem? Because part of the learning problem or the modeling problem is to define a P of x given Z and a P of Z. And these two things are the most important things because they define the model that we are working in. And is that sort of the question? Mm-hmm. Okay, so maybe there's a key point to make here. This P of Z is always something you decide. As I said, probability is about that degree of belief. This probability of Z is the probability assigned on models before you see any data. The question you are asking is how do I compute P of Z given X after I have seen data? So the key question here is that I know P of Z. It is a Gaussian distribution condition on Z. And maybe there's a neural network inside which transforms Z to the distribution of F. I know P of Z before I see any data. It's also a Gaussian distribution. Now, after I see data, I need to explain the model. I need to know P of Z given X. And that question is very difficult. As I said, because there's a complicated nonlinear neural network, I won't know the posterior distribution. And so I can't directly compute the posterior distribution. Because of that complexity of the neural networks living inside, I can't compute the integral even. because if I could compute the integral, then I would have p of x, all the parameters would live in p of x. I would just take the derivative of p of x directly and do the learning problem there. So all of this is coming because I can't compute the integral, nor do I know the posterior distribution. But after doing this trick, I can manipulate it, so now in a way that I can work with something simpler that I can learn that lets me include the evidence of the data that I actually have. Another question on this trick? Okay, we have another fun trick, so let's move on. Maybe we aren't going to get to the part on generative models that I actually wanted to talk about, but that's fun. So this one is also pretty important. This is one of the core tricks of what I called indirect inference. So Maria was just saying that I don't know p of x, and maybe I should just compute the integral of p of x or know its posterior distribution. And so this kind of way of directly computing p of x or approximating p of x directly with the bound is very important. And that is very direct, because I directly target p of x or its approximation. But actually, that may be one of the most difficult things you do. So instead, maybe I should not compute p of x directly, but I can compute p of x in relation to something else. Because actually, again, as Maria was saying, I'm not interested in knowing p of x. I actually only want to use p of x or the bound on p of x to learn the model parameters. Right. So what you can instead do is compute the ratio of two distributions, p of star of x, or some unknown distribution, to my model distribution q of x. So this will be the basis of this indirect inference thinking, because it will turn out that computing the ratio of two probabilities is easier than computing the individual probabilities themselves. And so because that's easier, that will help us sidestep this difficult problem using those other tricks and then doing things. So this density ratio trick is very important. It says if you ever have the ratio of two distributions, p of x to q of x, you can compute the ratio by learning a classifier that distinguishes data from p of x and q of x and computing the ratio of these two classifiers. We're going to derive it together, so bring your paper again. But this density ratio trick is very important. It has been used for 50 years at least. Most recently, if you are working in generative adversarial networks, or you've heard of them, this trick is the core of generative models based on generative adversarial networks. There are other methods like noise contrastive estimation, another class of methods called approximate Bayesian computation. The core of two-sample testing will always be involving computing this ratio, because the theory of two-sample testing and the Neyman-Pearson lemma tells us that the best way to do a test is to compute the likelihood ratio between the two of them. And then if you are thinking about covariate shifts, how you calibrate your models, this is going to be pretty useful to you. So let's do the following things. There are two distributions, the orange and the blue one, and let's sample data from both of them. And let me assign, because I'm designing the probabilities, I can do whatever I like, any data that comes from p of x that I sampled, I'm going to assign the label +1. Let's assume this is the data set. Everything in your data set, you're going to assign +1. Now, let's say you also have your model, and you can simulate data from your model. I'm going to assign to all the data from my model -1. And now I'm going to try and compute the ratio. Okay. Now, there's an important equivalence here, that the probability of the data that I have is just equal to the probability of x, given that the label y is equal to 1. Is that sort of clear? This is a very important line to make. I designed the label, so of course when the label is 1, the probability is p of x, and so this statement is true. And conversely, if I got data from this other distribution, q of x, if its label is -1, I'm going to rewrite this distribution, q of x given -1 is that clear? There are a few nods, but maybe we're going to do it in the Q&A on this section. Okay, so just remind yourself, the key question we are interested in is computing this density ratio, p of x divided by q of x. And the key tool we're going to need is Bayes' rule. So compute p of x given y. And Bayes' rule, again, is the rule for inverting probabilities. So I'm going to do p of y given x times p of x divided by p of y, and I'm going to jump between the two. So let's apply Bayes' rule. So this is the conditional probability we're interested in. It's the question p star of x divided by q of x. Because of this equivalence, I can just rewrite it as p of x given y equals data from class 1 divided by p of x from class -1. Okay? I'm just going to use Bayes' rule. I'm going to invert those probabilities. So instead of p of x given y equals 1, I'm going to turn this into a probability of p of y equals 1 given x. And so on both sides, you're going to get the top side is P of y equals 1 given x times P of x divided by P of y given plus 1. That is this top probability divided by the same thing for minus 1. Now, if I sample the data equally, then what will happen is that P of y equals plus 1 and P of y equals minus 1 will be equal. So if I sample 50 data points from distribution 1 and 50 data points from distribution 2, these two marginal probabilities will be equal, so they are going to cancel. And P of x and P of x is obviously the same. It's the real data distribution, so these two things cancel. So then what you're left is this expression. So it says, compute a classifier, take x, classify it as 1, know its probability, and divide by the probability that it's not 1. So this is the core identity. So the trick here is that it tells you that computing a density ratio is equivalent to the problem of class probability estimation. And so whenever you see these density ratios, you can jump to a class probability estimation. And everything you learned from Mustafa and Naila yesterday is that we are very good at learning classifiers. So this is something that you can always do. Is there a question on this density ratio trick? Yes, Vihan. Okay, so I just hit a step that I said, if you call this thing pi, the probability of P of y equals 1, because probabilities must sum to 1, what is at the bottom is just 1 minus whatever is left. So you can rewrite this as P of y equals 1 given x divided by 1 minus P of y equals 1 given x. And that's what's written in that particular paper. And actually that paper has one other thing. It says it allows for the two data sets to be imbalanced. So if you don't sample the first class and the second class equally, you can correct the imbalance of the classes by just putting the frequency of the two difference and these numbers. Another question on the density ratio trick. Yes? Yes, the kind of way, so the question was, does this work if you have more than two data sets? So this will take us into the realm of what we'll call multiple hypothesis testing and multiple testing. I think this is a very good research question, actually. Many people have not done this. I think I've only seen one example of where they've actually considered more than two data sets. And because it's going to get very complicated, the Bayes rule is not going to work out this way. So what we're going to do there is then unpack it using the law of conditional probabilities and then try and do these tricks subsequently. So it may not be as easy to implement, maybe a bit more complicated, but I think that's a great one to just think about and explore a bit more. Another question. Yes, Roy. The bound, okay, yeah, so let's go back. Okay, so Roy's question is, I mentioned that the probability of P of x given z can be represented as a neural network. Can I just say a little bit more about that? So in 2018, if you are going to implement these probability distributions, usually that statement that I meant is sort of what will happen. And so, as I said, this probability distribution tells you what the probability is. It describes, it says it's a Gaussian distribution of this variable x given z. So now a Gaussian, for example, has a mean and a variance. So this mean and the variance are dependent on the variable x, on the variable z. So what we need to additionally describe is how we get the mean and the variance of the Gaussian given the variable z. And so how we get the mean is a neural network. So what we do is inside here, there is a function which is a neural network that takes z in, and the outcome of that neural network is two things, a mean and a variance. That mean and the variance then becomes a distribution, and then that's what we compute. Or if it was a Bernoulli distribution, it would just be, it would just take in data and outcomes a probability like we need for this ratio trick. And that's how you can do it, and you can do this for almost anything. But because there are these neural networks, if it was linear, you could do anything because linear functions are easy to manipulate. But once that mean is non-linearly dependent on z, that's when the complexity of computing this integral comes in. That's why you can't do it in closed form. That's why the conjugate distributions don't work anymore, and that's why we need these tricks. Another trick. The ladies are very quiet in the room. Any questions? Yes? Are we still on this or the next slide? Okay, so we're getting a technical question about how is it we design our models to actually use the data, and can we have models that will learn data and not ignore things? And I'm going to skip your question and we'll talk about this one afterwards. Is there another question about the ratio trick? You had a question in front. Shall I follow up with you? Yeah, P star is standard notation. P star is just a distribution you don't know. It's a distribution you only know because you have samples from it. So it's your data set. You don't know the distribution of your data, but what you have is the data itself, and the data are samples from that distribution P star. And that's why I'm writing it in that way. Q star is something you do know because it has parameters, and you can train and manipulate those parameters. Q star is the model you want to learn. Any other last question? Yes? Can you say again? So is this the P of Y? No. So so P of X and P of X is the same on both sides, so they are canceling. Mm-hmm. Yeah, so you're going to have to be very careful in the numerics. Again, you would never want to divide by... Ignore this graph. I forgot why I plotted it. There was a story three weeks ago about this graph, but I don't know what it's about. But yeah, you never want to divide by zeros, which is why when you get... One of the problems of training these kind of models is that when they become very confident that, yes, this is definitely class number 1, you get probability of 1, and then you start dividing by 0 because you're going to do 1 minus 1. And so the numerics of this kind of thing can be a bit difficult, and that sort of impacts in the algorithms that use this trick, like the generative adversarial networks. Another question on this manipulating the probabilities here. Otherwise, we'll move on to the last trick. Okay, the last trick is about computing gradients. Gradients are, of course, the most important thing. So what you have noticed, we are always talking about the expectation of a distribution of a function f under distribution q. And now I want to compute the gradient of that quantity. So I'm just going to write at the integral. It's the gradient of the integral of q of z with parameters phi times the function f of z with its functions theta. And I'm going to take the gradient with respect to phi. Now, the reason this is interesting is because this is an expectation under q, and q has the parameters phi. I can't compute this integral in closed form. I cannot use quadrature to do it. And q, because of that complicated relationship, because I'm doing the integration over z, I can't just take the integral through here and then just do stuff. And also, the second thing that I need is I need this resulting, whatever this gradient looks like, it must be in a form that can be turned into an estimator. It must be in the form of an expectation under some distribution of some function. And if I can do that, then I'm going to be able to compute the gradient efficiently. So this problem turns out to be the most important problem in all of computational science. In general, this problem is called sensitivity analysis because computing the gradient with respect to some parameters is called the sensitivity. And of course, in generative models and inference, this is the core question. But if you are in reinforcement learning, one would say that this is the core question of reinforcement learning as well. The same gradient is going to appear in reinforcement learning, and you will almost certainly see it in the afternoon. If you're in operations research and inventory control, where you are trying to model queues, you're going to compute the expectation of the length of waiting in a queue, and you're going to want to minimize the time in the queue. This exact integral, this exact question comes up. If you're doing Monte Carlo simulations for various finance problems, then actually this gradient means something in finance. In finance, this gradient has a name. It is usually called sigma or vega or theta. And those sigma, that gradient itself is an indicator of the risk of investments in certain portfolios. So knowing to compute this gradient both makes you rich, helps you advance science, helps you generate simulated data. It's the most amazing thing ever. So there are only two things in this integral, so that means there are only two things we can do to it. You're either going to find a way to differentiate the function f. In this case, the function f is called the cost, so we're going to try and differentiate the cost. Or you're going to try and differentiate this function q. The function q in this kind of integral and this kind of language is called the measure. And so when we try and manipulate this and use a trick, we're going to get two different kinds of tricks. We're going to get one trick which is going to call the pathwise estimator trick, is when we're going to try and differentiate with the function with respect to z. And we're going to get another trick, which is going to call the score function estimator trick, when we do the differentiation with respect to q. So I'm not going to show you the pathwise estimator trick. I'm going to show you the score function trick because you may use it in the afternoon again. But there are only two things, and in general, there are 4 classes of such gradient estimators that we can use, but the ones that are useful for machine learning because they help us do computation at scale are these 2. So let's, again, bring your pieces of paper. We're going to do a fun derivation. This one is really easy. So the score function, this technical word, a score function, is the derivative of a log likelihood function. So if I have log p of x, the derivative of log p of x is called the score. So here's the trick. You just use the definition of the derivative of log, the gradient of log of a function q of z with respect to phi, because the derivative of log is the gradient of the thing itself divided by q. This is the basic definition of the derivatives of logs, right? And so now we're going to use this thing everywhere. Wherever there's a gradient of a log, I'm just going to substitute, remanipulate the integral. So here are some useful properties. I'm going to give you 2 minutes to do this one yourself. I'd like you to prove that the expectation of the gradient of the log of q of z under this distribution q is equal to 0. And how you're going to do that is do exactly as I said, just plug the trick and remanipulate things. So just spend some time to show this. It should be 2 equations after this that you should get it. Just give yourself 2 minutes, scribble a little bit, think about it, and we'll carry on. You can work with your partners also. And if there are questions, you can come up to the mics already, and then we can pick up. Okay. Hopefully you at least got the first line if you didn't manage, or if you're looking over the shoulder of your friend. So let's just do it. Again, the point of doing these tricks is that eventually you will become so good that you will just look at that integral and say, it's obviously 0, and this is the aim that you should always aspire to. And how you will do that is by keeping these tricks in the back of your mind. So exactly, let's do that. The expectation of the gradient of log of q, if I write it out, is the integral of q of z times, use the trick, gradient of q divided by q. Magically, 2 things have cancelled. So q of z and q of z cancelled. And now I have the gradient of q of z, and I'm going to swap the integral and the derivative. The integral of the distribution is 1. The derivative of a constant is 0. And so this quantity is 0. And if you practice this a few times, you will exactly just look at this integral and, well, yeah, obviously, let's move along. And this thing becomes one of the most important quantities that we need, because when we do stochastic optimization this way, having this quantity will be useful for us to show unbiasedness, but it is also the way that we will be able to control variance, because it's a good term for us to manipulate. Another property of the score is that is related to this quantity called the Fisher information. The Fisher information gives us all properties around the variance of things, and it is the way of showing this Kramer-Rao lower bound that I mentioned earlier. So let's just derive the score function estimator. Again, bring your pieces of paper. Let's do it together line by line. Again, the integral problem is the gradient. So it's compute the gradient of the expectation of the function with respect to phi. I'm going to write out the integral. It's the gradient of the integral of q of z, which is the distribution I want to integrate with respect to, over the function f dz, so I didn't forget it. Now, the Leibniz integral rule is the rule which tells us that we can actually swap integrals and derivatives. Now, how you're going to think about that in your mind is that derivatives are basically limits, and the rule that we need to think about is when is it correct to swap integrals and limits. And Leibniz integral rule is one of the 3 ways of convincing yourself that it's correct to swap integrals and limits. But you can assume for everything that you're going to do this week and for the past few days that this is always valid for you, and there are some technical conditions for that. So I'm going to do that, and then basically I'm going to do the identity trick again. I'm going to multiply by q and divide by q. So the gradient is inside gradient of q f of z. That was what we had before, multiplied by q. So the integral is still exactly the same, right? Hopefully you're managing to scribble along with me. So now, the log derivative trick, I'm going to use it in reverse from how I asked you to use it before. I have a gradient of q divided by q. I know, because of the log derivative trick, that that is the gradient of log of q with respect to z. So now I have a new kind of integral, exactly the integral that is the form of an estimator, right? It's the expectation under the distribution q of the function f of z times the gradient of the log of q. So that's the gradient, and I'm going to skip this line. I'm not going to explain to you the control variate question. So this gradient here is the key quantity. It has many, many, many different names depending on where you're reading this week. So if you were reading when they introduced this in the 80s or so, this was called the likelihood ratio method. I don't like this name. I think it's technically incorrect, so I never use it. In reinforcement learning, they think of this gradient computation as an algorithm, and it's called reinforce, and it is the basis of the policy gradient theorem. In other areas of variational inference, they exploited this integral, and they call this black box integration. So, so when can you use this kind of trick? So this is a question that came up for many of the others. This is a very general trick. Let's stay at this gradient for a bit. It says that I just need to compute the gradient of the log of q, and because q is the thing I'm deciding, I can compute its gradient, and because it's a log, it's even more convenient. F of z is the cost function. I just need to multiply f of z times this gradient. So I can use this for any kind of function f. If the function is differentiable, I can use this, but if the function is not differentiable, I can also use this gradient. I don't need to know the function analytically. I just need to be able to evaluate the function f. If I can evaluate the function, give it a z, out comes a function f, then I can use this to compute a gradient of this distribution q. This is why it's called black box, because you didn't need to know inside the function. The function f is just a black box. The distribution q, which is the thing I introduced because of that was the thing I want to learn, needs to be easy to sample from, because I'm going to use the Monte Carlo theorem to sample from q and evaluate this over an average. And q needs to be differentiable because I'm obviously computing the gradient of log of q. But this will become really important, and when you do the reinforcement learning in the next round, you'll see this appear again. Are there any questions on this score function and the log derivative trick? Yes? The f of theta? Yeah, I'm just leaving the f of theta because, as I said, when you use this trick, you don't need to know the parameters of theta. You're not taking a derivative of theta. You're not computing anything about theta. You just need to evaluate it. So as long as you can know its number, that's all you care about. Another question? No? Okay. Yes. Okay, so I didn't explain this line, but one of the problems of gradient estimators or anything that you compute with Monte Carlo is that it is going to have a variance. And one of the things we want is to have low variance. The reason we want low variance is because we can use the least amount of data to do our learning. If we have high variance estimators, we're going to need a lot of data, and a lot of data means it takes a lot of time, and data is also expensive. So this C is one way of helping us reduce the variance around which we compute this kind of quantity. So C can be a constant, in which case you just call it a baseline, but there are many other things we can use. So you can see that it's f of z times gradient of log, which is the thing we had before, and now I'm subtracting something minus c times gradient of the log, but you know the expectation of the gradient of the log is 0, so this thing doesn't actually change the gradient, but what it will change is its variance. Another question? Okay, let's go on to the generative models bit in 10 minutes. Anyway, the point of all of this was that please continue to strengthen your probabilistic dexterity. Get used to manipulating integrals. Use those identity tricks. Use those bounding tricks. There are many other tricks that we could have spoken about, but I'm going to skip them. So let's do a very brief view of generative models. We're not going to have time for you to look at them, but I'm just going to describe them and talk about their applications, and then we'll end there. So the point of thinking about generative models is that we want to move beyond classification. I'm not just interested in assigning inputs to outputs. I want to do more than that. I may not have those outputs. I may not have the label. Another thing when we want to move beyond classification is asking about that question about how we recognize objects in the world, how we know that things can vary, and how we can detect that kind of variation. Are there concepts in the world? Are there ways for us to establish those concepts? How can we use those concepts for reasoning and decision-making? Can we understand the world? Can we simulate it going forward? How can we detect surprising events in the world? And can we anticipate and generate rich plans? These are all the questions that are going to come up when you want to move beyond just solving the problem of classification. And this is where the problem of generative models comes in, because generative models gives one tool to tackle all of these questions in one way or the other. So what is a generative model? It has many, many different definitions. They're all compatible. You can just choose the one that works best for you and that helps you think the best. So the simplest one is that a generative model is a model that is a simulator of data. It is a way of us to learn a simulator of data. So if I have complex climate data or weather data, I need to learn a simulator of the weather. A generative model is the thing that you can use the weather data to then learn a simulator, and then you use the simulator afterwards to do things. Another kind of way of thinking of a generative model in the technical definition is that it is a way of doing density estimation. Data points are things we observe as samples from an underlying distribution. If we want to learn that underlying distribution, then that is called density estimation, and that's what generative models help us to do. And in general, generative models relates to everything that we want to call unsupervised learning, whether that is the sequential models that we spoke about yesterday with Kyung-Hyun, or the other kind of mixed models that I'm talking about now or later on. So their characteristics that these are probabilistic models. If we need to generate data, if we need to represent the variation and uncertainty in the world, they will need to themselves be probabilistic, and so probability is going to be very important there. They are typically very high dimensional. It is an entire image. It is a whole frame of video. It is a big spatial temporal data set. There was someone here with an amazing poster around Fane-Boss modeling over the whole of the Western Cape. That kind of spatial and temporal data is very large, and what we are interested in is targeting the distribution of the data, that quantity P of X. And if we know that quantity, then that is basically the definition of unsupervised learning, because we were never given a label. So I think about the applications of generative models in three different areas. One of them is about products, and we have several kinds of products that we want to do. We want to be able to do super resolution over low bandwidth channels, or compression, or we want to do some kind of text-to-speech where we want to generate language. I think there's a great area to do more product work. Of course, generative models are important for us to advance our thinking of science, whether that's in proteomics, in the sequence of drug discovery. I spoke to someone's poster thinking about that question. Many of you who are working in astronomy or high-energy physics, there's also a role for generative models in this case. And of course, for those of us who are working in solving those questions of intelligence and the principles of reasoning and intelligence, generative models have that role to play in thinking about planning, in how we explore environments and worlds, how we equip artificial agents with self-motivation, what we call intrinsic motivation, how we can do model-based reasoning. So let's talk a few of them. The first one I think is really exciting. If you have an Android phone, you have this kind of generative model living in your Android phone. They are the ways we build assistive technologies. So assistive technologies are those technologies which help us live our lives easier, people with speech impediments or anyone who is having difficulty. This is a generative model that takes in text waveforms. Actually, it depends on how we build the model, and it generates speech and voice. So if you have the Google Assistant, this kind of generative model lives there, and this kind of model there is what we call a fully observed conditional generative model. And so that's one of those text-to-speech is one of the great ones. This is the example of the model called WaveNet. The other one is sort of compression and communication. when we have low bandwidth channels or when we need to send things in a secure way, we can use generative models as a more general way of thinking about compressing data and images, sending them over channels, and then decompressing them. So this is an example from some friends on super resolution GANs, where you have an image and you want to send it at much higher resolution. The kind of things they were thinking of when they were working on this project was about doing live streaming of cricket matches over a phone, where you want to send it in very low resolution and on the phone get HD definition. And so that's what people wanted to do, and you can do other kinds of compression algorithms around that. There's another area, I'm calling it generative design until I find a better name for it, but you can use generative models to help in that kind of human-centered way, a way of thinking about designing new things. So we can have generative models of objects and chairs or other kinds of human-based environments. We can rotate them. I think we could see a way of using generative models to create this very flexible, fluid, augmented reality on the fly based on things we think about. There are many people who are thinking about this chemical synthesis problem. How is it that we can create new chemical molecules, synthesize them in the lab, and use them within the experimental design framework? So I think that's really fun. Here's a video from someone doing a PhD in London. His name is Memo Akhtem. It's not a machine learning in the technical sense that I'm showing you now, but more an artist and thinking about how technology and art intersect. So this model is a GAN, which is trained on several images, and it's conditioned on this image on the right. And they just put objects underneath, and then they see how it actually gets generated. And then they look at all the different kinds of variations. And I think it's quite mesmerizing to look at these kind of things, and the kind of creativity that when we develop our technology and we put them out into the real world, other people pick them up and they use them in ways that we ourselves could never imagine doing. So I think I want to forward to this video to see if you can get the bit with the fire, which I think is really fun. Okay, so here's a charge. It's like Sauron doing something evil. And yeah, hand on fire with the foam charger. I think this is a very fun project. Okay. There are many of you who I spoke to in the room also who are working in these difficult questions of science. The African contribution to big science obviously is happening here in South Africa and various other places. So whether you are working with the cosmology mass map, which is something like here, or you're doing calorimetry experiments at the Large Hadron Collider, or you are taking images of galactic images, you can use generative models as having a role to play in understanding these large quantities of data that we are generating, helping us simulate them go forward to understand how they will behave and how they will change over time, or even understand different characteristics of the evolution of space and of ourselves. So there's a lot of interesting work happening in this area. And of course, as I spoke to many people, healthcare is one of those important areas where we are seeing generative models come into play. If you are working in imaging problems, we're using generative models as a way of expressing to physicians, to doctors, what variations of segmentations of images are. So if you have tumors like in this image, the tumor may have various ways that you can identify the tumor. We can use generative models to explain what that variation of the tumor is so that they have more confidence in using these kind of technologies. We can use generative models to understand the patient pathway through a hospital, understand the different challenges to maybe make a prediction or alert of when certain things may go wrong or bad. And so this is an example of sepsis and making predictions of sepsis in real time. And in there, uses a generative model to help understand the cause and effect of a disease and its outcomes. So that's really good. I think I have 5 minutes left. So I'm not sure what to do. I'm going to skip a little bit. Maybe I'm just going to end there. I think there's a huge space of things to do in generative models. We're only just beginning our work in this area. I'll quickly skip through the slides to show you the things we would have spoken about. And we can talk about it for the rest of the week, of course, at any time. Latent variable models. These are the VAE models, if anyone wants to talk about variational autoencoders. There's the GANs, the implicit generative models. We're going to talk about rethink about the model inference algorithm principle within these two classes of models. We're going to think more about derive the GAN algorithm together and think about other related algorithms related to GANs. And we were going to think again more about this model evidence and think about variational autoencoders as one way. I'm going to just skip to the end, which is the very last slide. Okay, so please, if there's anything, I hope you have a small bit of excitement about the work of thinking about probabilistic models. Please continue to think about models within that framework of models, of inferential principles, and of algorithms. There are many applications in both products, in advancing science and advancing AI, where generative models have that role to play. If we had time, there are many interesting examples that we've worked on in variational autoencoders, as well as adversarial networks and other kinds of things. And thank you for your attention and all the questions. Are there any other questions that have come up in your mind that we want to talk about? There's one over there. And over here. Maybe you can walk over to the mic in the meantime.
I'm just curious, do you know of any ways to check if the generator has actually made proper images or data? I know there's an FID score for images, but then specifically not images data, like you're making data that could, you just may be making the same data that's already in your distribution. How do you check quality of data, and specifically not images itself as well?
Mm-hmm. Okay, so the question here is about how do we actually evaluate our generative models and probabilistic models in general. And the key concern that was coming out is, what if the model just memorizes the data that we have? It's not generalizing in the way that we expect. It's actually ignoring some parts of our data. And actually, I don't have a good answer to this question. It is one of the most difficult questions to answer right now, and one of those core research questions is about evaluation of generative models in general in different domains. So this is why I say to work with your domain experts. So the domain expert will have several other characteristics of those data sets that are interesting that you assess. So for example, if you are working in that drug discovery domain, then when you synthesize a molecule, there are several different measures of quality that you can use over a population. You have to know that certain bondings have to happen. You can check the hydrophobicity of certain things. You can compute certain angles. And based on those measures of assessment, you can do that. Similarly, if you're working in climate, climate has had this problem for several years. They have entire teams of people just to do this evaluation, where when you generate a simulation from a model, you then calibrate it or look at how it relates to the real world, and then they have several things. They are called validators and forecasters who use their expert knowledge about the rules of physics and what should happen to then answer those questions. So if anyone wants to think of a difficult research question, the difficult research question in this area is about evaluation of generative models, and there are other proxies, the fresh air inception distance that you mentioned and others, but they're very specific to images, and so don't generalize to others. There's a question over here.
Thanks, Shakir. I think my question is about how you would use generative models in a semi-supervised context. So you talked a lot about where you have observations from your true data set or your true distribution. Could you maybe just give us some thoughts on how you would deal with that, where either class labels or just certain observations from your data set have missing values or something like that? So that's a common issue that we face.
So the question is about how is it that we can use this kind of generative thinking to do semi-supervised learning. So semi-supervised learning is the problem that mixes both the supervised learning that we were thinking about yesterday and the unsupervised learning that I'm thinking about today, in which you have a large data set, but only a small subset of the data has some labels. And actually, there is no difference in the thinking that you do by building this model, which is why I actually asked in the beginning for you to think about building probabilistic models. And how you would do that is to build a probabilistic model that is a generative model over the data. And on the side, effectively lives another model which accounts for, when you do have data, what the impact of the label is. And now, what that integral, the question of asking and writing all those integrals is that when you have any data point that doesn't have a label, those sections need to be integrated out, and then they don't influence things. And when you do have labeled data, then you use that to learn the parameters of the distribution. So I have one paper that we did to work on this that we can talk about a lot more. And there's a lot more work around how we design those models, the kind of deep architectures that we use, ladder networks, for example. And I think semi-supervised learning is one of those core questions of moving forward to a big question in the field, which Nando mentioned on Monday, which is about data-efficient learning. How is it that we can learn efficiently? And advancing semi-supervised learning and understanding the structure of that data, combining in this is what we need. There's another question over there.
Yes. Hi. Thanks for the talk. I wanted to compare like the generative, the GANs and the variational autoencoders to restricted Boltzmann machine, and how they are, how those are better than the Boltzmann machine, and why.
Let me just move a different slide that we can use to talk about that. Okay, let's use this slide here. So I asked you to think about models and inference and algorithm. And the question that is being asked is that we have, so the first question is that we're going to talk about latent variable models. So latent variable models are these models with the green circles. They introduce something which is unobserved into the model, a hidden variable. So the first part of his question is about how can I compare different kinds of latent variable models. And then specifically the question he's asking is that we have two types of latent variable models and their corresponding algorithms. The algorithm that he mentioned specifically was generative adversarial networks, and the other algorithm was the variational autoencoder. And how did those algorithms relate to algorithms like contrastive divergence? Is that the right way? So there are several things to say about it. I already just explained that there are latent variables underlying, so that is what's common between them. One of the biggest differences is the fact that the implicit generative models that are used in GANs and the prescribed generative models that are used in VAEs, they are directed graphical models. And whereas the Boltzmann machine fits in this other class of models, which are undirected graphical models. So in one case, you get to choose the direction of causality. You say specifically that a variable z causally influences the data x. And this is actually a very powerful piece of knowledge that you have, because that means, as the question came up earlier on, you can write the probability distribution P of x given z, and you know it, and you always know it, and you can manipulate it using the tricks that we did. So the Boltzmann machine, or these undirected models, don't do that. And they are very natural, of course, in other settings. If you were modeling, as they do in physics, a lattice, there's no necessarily any causal direction. Things are connected or they are not. And so in those kind of settings, these kind of Boltzmann machines or energy-based models become much more important. So now the key difference is once you are in that realm, the kind of inferential principle that you need becomes very different. And here it is actually turns out to be easier both in practice as well as theory to build models, to build very rich classes of models, to scale them up to very large data sets with these directed graphical models, whereas with the undirected graphical models, they have very difficult time scaling to large data sets. We don't have good ways of doing deterministic computation. We have to do lots of Monte computation, which means things take a very long time. They have high variance, so there's still a lot of research to do in undirected graphical models and Boltzmann machines in general. Are there more questions? Yes. Okay, so the question is, how is it that generative models and in general probabilistic models help us think about causality and the way that we can learn about cause and effect from data, and how is that different from supervised learning? So let's look at this example here. Supervised learning makes a key assumption. It says that when I have data x, the number is 3, and out comes a target, a label y, there's a very important assumption. The assumption is that there is an underlying source of noise, of variation in the world, but that variation is not the same. It's independent between the input and the output. Now, a causal system is something very different. A causal system says that there is a source of noise which is the same between the input and the output. And one of the key things we have to do when we build a model is we have to understand whether or not there is this source of noise, or what is sometimes called a confounder, which is influencing both the input and the output. Because now you can see if there is a source of noise that influences both the input and the output, there are two ways of affecting the output. I either change the input and then that changes the output, or I change the noise and that changes the output. So that's not a way of doing causality. So the way you would have to do that, there are several ways to do that, using the tools of generative models to build causal models. One of them is called the counterfactual inference, or building counterfactuals. What you will have to do is learn the model of one causal path. That can be a generative model, and you need to learn a generative model over the things you have not seen. The things you have not seen is the technical word of the counterfactual. So that's one way of doing them. The other way you can do them, and using the tricks that we have done, is to use a method which is called the instrumental variables technique. Instrumental variables technique will introduce one other new variable. That new variable is the thing that will decouple the input with this common source of noise. And then generative models are a way of learning new kinds of powerful instrumental variable models. Another question? Yes, round two. The ladies are still very quiet. I'm very disturbed.
I'm working with GANs at the moment, and I don't know if you also have been, but every single paper I've read has always got the same sentence of GANs are difficult to train, and then they don't really explain how they train it, and they just show the results. I don't know if you have any advice of when I'm at that point of I'm struggling to train it, what do I do now?
Yeah, so I've done a lot of work in GANs over the last year or two now, and it is true that they are difficult to train. Unlike a variational autoencoder, the first time you do it, they just sort of work. They may not generate images if you are working the image domain as well, which is why I think it was the thing that I wanted to put forward to you was to think about those underlying tricks. If there is the density ratio, which is the cause of things there, then some of that problem of instability relies on the issue of computing those density ratios and the problems of computing density ratios. I think the other reason that I wanted to stress was that the importance of us focusing on those inferential principles helps us explain what's going on. So when you think about it as this indirect inference principles, then you will understand that the way we are training GANs is by creating a large set of feature vectors, and then we are comparing feature vectors between the real data and the training data. And the way we are doing that feature vectors by building the classifier. So some of the asymptotic theory will tell you that you need to do that. You need to minimize the variance that we are computing by computing those features. And this is where you see things like the gradient penalties coming through, and much of the thinking of the work around gradient penalties. The gradient penalties are really amazing. I think they've always worked. We have continued to use them. There's a lot of sensitivity to the architecture, the specific architecture that you have. And actually, if you have a very good DC GAN, in this particular case, a very good DC GAN is probably the strongest baseline that you have. But I'm going to defer this question. Martin Arjowski is in the room, or he's around, and I think he's better than me to even comment on much more technical details. And then we can talk later also about some of our other experiments. More questions? No? Okay, thanks. Thank you very much.